Hi guys, welcome back to the series of system design interview preparation course prepared by me. Um, Today we're going to cover about one of the important concepts in distributed system. It's about the hashing. I'll introduce both the traditional ways and the what's the problem with that, and also of course the solutions to those problems, the new way called consistent hashing. Before we start, I just want to point out the videos are specifically made for you to ace your system design interviews by building a muscle memory. So you can have like reactive response or a robotic response to provide those answers either by explaining those concepts or utilizing those concepts in the system design interview. So a lot of things are hidden from the just to keep this simple and more memorable. Okay, let's begin. So hashing, it is used to support distribution of data across different servers. So for example, if you have 100 key value pair or 100 data points, you want to spread across 5 servers, probably want to save like 20 on each of the server to distribute the load. And so that's exactly the purpose for hashing. It's super helpful in horizontal scaling. And traditional way is just a key multiply by the number of servers. So as I listed out here on the left-hand side, we have 100 keys. We use like multi-based hash functions. It's basically hash the key multiplied by the number of servers. So if 100 keys spread across 5 servers from 0 to 4, each server will have like 20 data points or keys stored there. That is good mapping. So simple and easy peasy, job done. But as always the case in software development, if things are not changed, things are not failed, there are not errors, either intentional or intentional, software engineering will be much simpler, but it's not the case. So there will be always case as a result, there will be server or node needs to be added or removed, rebooted, software updates, etc. So as a result, we are adding or removing those quite frequently in the production environment. So in the traditional way of hashing, say this example, we're adding a new server. So there's two problems with that. First, we'll recalculate all the keys based on the new hashing function. It will be multiplied by 6 instead of 5, so recalculate everything. And then as a result, inevitably, we are going to redistribute nearly all the keys. As you can see from the example illustrated below, only the keys of like 0, 30, 60, 90 are remained on the same server, compare like when the number of servers are 5. So a similar case for server number 1. If you can take a deeper look, there's exactly 4 keys will be remained on that server compared with like when we are having 5 servers. So from mathematics perspective, the calculation can be based on the great common denominator by the number of old servers and the number of new servers divided by the number of old servers. So exactly 80% of the keys needs to be redistributed to other servers. So imagine if you have like 1 million or 1 billion keys, the amount of work, computing, storage, redistribution, it will cost a lot of overhead. So that's exactly why we want to do something new, like more efficient, that involves less data movement in a distributed system. So before we move on, I think there's a question for you just to think about like the case of like removing a server, what percentage of data or keys needs to be redistributed. Please let me know in the comment. So consistent hashing. A few key concepts here. The first, we need to have like a hash space. Hash space is provided by the hash algorithm. Is the total range of possible outcomes. So in the case of the SHA-1, because it's like 160-bit hashing at output, so it support each bit has like 2 possible values. It supports the 2 to the power of 160, of course, minus 1. And so that's the hash space comes with SHA-1 for different hashing algorithm, the space would be different. You can pick the one most suitable to your case. If you have smaller scale, probably you choose one that have comes with like a smaller hash space. So in this case, if we use SHA-1, it's from x0 to xn. It's the number of possible values on the hash space. So in reality, could be millions or even billions more. And once we have that, if we connect the end to the start, we'll get our hash string. And then there will be three things we need to do. First, same as the additional step than the traditional hashing method, we will also hash the server or the nodes by IP, by name, like by certain identifier, and it will be mapped on the hash string. And then the second step will be hashing the keys. So this one is similar. Only difference is like we are using a different algorithm to do that. And so the key will be hashed and mapped on the hash string as well. And when it comes to server lookup for a certain key, for example, we will go clockwise. So for example, let's see this would be like key 1 or key 99. We go clockwise. Now we find, okay, the closest one is server 2. So we know like this key will be stored on server 2. And so for again, key 1, we go clockwise, will be stored on server 1. And so key 2, server 3, etc. And probably you will see there are a couple of problems given this design as well. So first is how do we make sure like the servers are distributed evenly on the ring? I think the first challenge. And the second challenge is like how do we make sure or increase the probability like we have evenly distributed keys at each of the section. So where like each server will handle pretty much like evenly number of keys in this case. So whenever there's problem, there's comes a solution. In this case, the solution would be the virtual node. So what does virtual node mean? Instead of like we only hash the server or nodes in a one-to-one mapping on the hash string, we are adding like a few we are instead of adding one, we are maybe adding three as replicas or virtual node for a particular server. And we add them to the mapping ring. So for example, for server 0, we probably have like three virtual nodes distributed on the hash ring. And for server 3 or other servers, we can do the same. The benefit for this is like it will produce a more evenly distributed server. And also we can assign different number of nodes for based on the capacity or the power or storage capacity for each of the server. So for example, if server 0 is more powerful, like have like more storage space, more powerful RAM CPU, we can assign maybe 5 or 10 virtual node for server 1, but server 3 might be less powerful. We can only assign 1 or 2 based on the use case. So in the system design interview, it won't be like go into too much details how to fine tune this, but in production, it will be like based on like a data, based on access pattern, how do we see that we can do the fine tune. But knowing all this about like virtual node, how it is mapped in the hashing ring, that would be quite enough to succeed in the system design interview. And so yeah, with the virtual node, you can see it will be like more evenly distributed. The server will be more evenly distributed across the hash ring, and so will be the date will be like more evenly distributed, which goes to which server. And now we can calculate. Don't forget, the main reason we are introducing consistent hashing is because of like things changed. Either code can be added or removed, and we want to make sure that there is minimum movement of data in the case of that. So let's just assume that would be, let's say, like keys are evenly distributed, or this is pretty much the case in reality. And then, like, say, let's try to add, oh no, key, add another key. So as we previously said, like one for each key, we go through clockwise to find like which server it stores on. So in this case, for example, if you want to remove S2, so the key, let's say key 1 goes to S2, and then we are going to remove it. It will be removed from the ring. So it will go to the next clockwise, find the next closest virtual node. So in this odd node, this case, it belongs to server 0. So now like key 1 will go to server 0. And as you can see the benefit for that, there's only a limited number of keys needs to be removed. Whatever was stored on the virtual node S2 or any of the replicas it stores. So it will be the same case when we try to add a new one to the ring. So for example, if we're adding, say, here as maybe as 4, 1 is a virtual node. Oh, too much space. Yeah, when we trying to assign or find the keys on the ring, it instead of going to S2, it will go to virtual server for one of the virtual server 4's node. And again, as we keep it to the minimum. So as maybe you already figure out the actual number in your mind. So the actual movement we take is like the number of keys divided by the number of virtual node, more or less that. So for example, if we have 100 keys, like 5 servers without virtual node, probably only like 20% of the keys needs to be distributed. If we have like more virtual node, like say like each server has like 2 virtual node, then it will be like 10% of the data needs to be moved. So you can see the huge difference between this new way and the traditional ways. And then, yeah, let's maybe write some code just to illustrate that. So it's like semi-pseudocode. We have like this in C#, we have like sorted dictionary. For other programming language, there'll be like a different structure to store this. So what behind this is just a black write tree. So it's like self-balancing. It has certain rules. If you are interested, you can Google about that. But I think for us, as long as you know, it's kind of like tree structure, it would be sufficient enough. Then for each node, as we said, there'll be virtual node. They has 3 replicas, and we have like a hash algorithm. You can use MD5, SHA-1, or anything you want. So we can just compute the hash. So get the hash is simple. Just for each algorithm, you can compute the hash, of course, into get from the bytes and then return to int or not, depends on the design choice of the actual case. Then for the ith node, it'll be like given we have replicas, so we want to make sure we have 3 replicas. So it'll be a for loop from 0 to 2, let's see, and then we calculate the hash. We call the get hash function with the node key. Oops. Yes, we need to pass node key. Could be string or int, doesn't really matter. Like to illustrate as an example, then we get the hash key, we add it to the hash ring. That's the first step, as we illustrated here. The first hash server of a node of add one. Ring hash equals node. And then remove node is again, it will be the same thing. We calculate the hash, remove it from the ring. Here, yeah, maybe plus I is the either 0, 1, or 2. Same thing here. right? And then get node. So if we have a key like where should be mapping on, or which node should it be mapping to? This one would be like double check for empty. It's if the hash string is empty, then of course return nothing. But if it has something, we first again calculate the hash for the key, of course. The key. And when we go through the hash string, we find the smallest mapping. Remember, this key is the calculated one, the hash for the server. So if we find one, then is the key is mapped on that node. The value is the node, right? And if there's no mapping or it's not found, it's a loop around the ring. We return, I think, maybe just the first ring. So simple enough. It's like just for illustration purposes, what would happen when you add a node, when you do the hashing, remove node, get node. If you want more details, like leave a comment. I can certainly provide like more information on this. So yeah, I think that's pretty much for the hashing and also like why consistent hashing is the choosing way like to distribute the key evenly in the distributed system environment, and also like why it's efficient when you are trying to add and remove node. All right. Thank you for watching. See you guys next time.